Hi everyone, in this video we are going to finish section 4.3, absolute extreme points. So absolute extreme points is very different from the, and not very different, it's slightly different from the relative extreme points. So first, before we start a new section, let's go over the, excuse me, not this one. Let's go over on section 4.2, the relative extreme point. For a relative extreme point, for example, first, let's say a relative maximum point. So we say a function has a relative maximum point at input C. Two conditions. First one, in some open interval. That means we can find an open interval around the point C. So that means the two endpoints, they cannot be relative extreme points. And that is the first condition. And the second condition, that point, the function value is greater than or equal to any other output. Pay attention, not the whole interval, but actually just in some open interval around point C. So that means from this sentence, we know that actually for a continuous function, we can have many we can have many relative extreme points. So for example, like in this one. So you can see here, based on the definition, we have two relative maximum points. This is the first one, this is the second one. Because if you draw any open interval, then you can see actually that point, the function value is greater than any other function values around the point, but not including this one. So this one, the function value is greater than any other point around it. But you can see this one, the function value is higher than that one, but actually that one is not the point that around the first point. So the second condition is very important in some open interval around C. First, we can actually get the open interval. And second, around C. You cannot go too far, including all the points. That is impossible. That is a different definition. That is called a absolute maximum point. That is in next section, section 4.3. So that is a relative extreme point. And pay attention to this one. For the two endpoints, A and B, the 2 points, special points, point A and point B, they cannot be relative extreme points. So for the relative extreme points, we don't consider the two endpoints, A and B. Pay attention to the to this property. The two endpoints, they will never be relative extreme points, but they can be absolute extreme point. And then the second part is a critical point. The second definition is about critical point. Critical point, we have two cases. So first one, if the derivative is 0, then we can say this point is a critical point. Or if the derivative does not exist. Does not exist, we have three cases. If the function has a vertical tangent line, then the derivative does not exist at the single point C. Second, if the function has a sharp corner at point C, then the derivative does not exist at the point C. And the last one is if the function is not continuous, for example, like this one, the function is not continuous at a point, then we have a hole there, then the derivative at that point C does not exist. So two cases. First, the derivative does not exist, and second, the derivative is 0. So no matter which one of the two cases, then we just say, all right, this point is a critical point. And then, so this part shows you that actually the critical points gives you all the possibility of the relative extreme points. So that means if for the other relative extreme points, they must be critical points. So, but it's not necessary to say that all critical points are just the relative extreme points. That is not correct. So actually, this is just the one direction. It's not two directions. This is not an if and only if condition. So this one, you can see if f has a relative extreme point at C and this one exists, then we have the conclusion that the derivative is 0. However, if we only have the derivative is 0, it's not necessary to say that actually you cannot just say that we have an extreme point at this point C. And then this part is about the first derivative test. Just remember, for the first derivative test, we only use it for Alright, now you have several options, critical points. You are offered a lot of critical points, and you really want to know which one or which several of the critical points are actually relative extreme points. So we use the first derivative test to determine whether a relative extreme point occurs at a critical point. So that means if, alright, we have 3 critical points, we want to know which one is actually the relative extreme point. You have to check it one by one by using the first derivative test. So let's see next, go over what it is. So the first one, because now all the options are critical point, so it must be a critical point. For a critical point C of the function f, that is continuous on some open interval around C, so that is continuous, that's of course. If the derivative changes from positive to negative, so positive, if the derivative is positive means the function is increasing. If the derivative is negative means the function is decreasing. So increasing, decreasing, then actually you can see here, this special point is actually a relative maximum point. So it must be relative maximum, and similar relative minimum. And then the last case shows you if the sign of the derivative does not change. So that means this is the first case. The derivative function, the slope function, is a constant number. Constant function, or you can say. And the second case, even though it's not a constant function, but the sign is always positive or always negative, the sign does not change. So 2 cases for this part. The f prime does not change sign as x increases through C. So the conclusion for this condition is that the function does not have a relative extreme point. So actually we just check if the sign of the derivative changes. This is the theory part. The sign of the derivative changes. And what does the sign changes mean in a function graph? That is this part. Graphically, you can see this part, the highlighted part. If the slope, because for this one, you can see all of them are actually talking about the derivative. If the f prime of x, or if the slope graph crosses the input, the x-axis at that point x equals to C. So that means for a critical point C, if we want to check if a critical point C is a relative extreme point, you can just check f prime of x to see if at a single point C, the function, the sign changes, the derivative sign changes from positive to negative or from negative to positive. If the sign changes, then actually this critical point is a relative extreme point. But not just the touches right here, not just the touches. What the touches mean? C. So you can see this one, just the touches. Actually, the sign does not change. So for this one, this point, the conclusion is right here. If the crosses, then we can say this point is a critical point. This point is a relative extreme point. Then and the second one, for a function that is continuous on an open interval around C, with the derivative does not exist. If the slope graph is on the opposite of the input x of the x-axis at that point C, then we can just say, alright, we have a relative extreme point. And the last case is if the function is not continuous. If the function is not continuous, then of course that is one of the counterexample that the derivative does not exist. In other words, the function is not differentiable at point C. So in this case, you can just examine the graph. But because if this condition does not satisfy, it is still possible for the critical point to be a relative extreme point. So it is still possible. So that means you still have to check the function graph to see if this point is a relative extreme point. So that's all for section 4.2. So 4.2, just remember that the two endpoints, point A, point B, they cannot be relative extreme points. For example, two endpoints, point A, this point, cannot be a relative maximum point. This point also cannot be a relative minimum point because they are endpoints. And at the two endpoints, we actually cannot draw an open ball that covers this point because the left side is out of the boundary. So next, let's go to section 4.3. So 4.3 is a new definition which is similar, but on the other hand, they're different. This is a absolute extreme point. So first, of course, similar. We've learned that for a relative extreme point, we have relative maximum and relative minimum. And similar for the absolute extreme point, we have absolute maximum and absolute minimum. So let's see the definition. A function f has an absolute maximum at input c if the function value f of c is greater than or equal to, the keyword here is actually the not this one, every, and similar for the absolute maximum, then every other output value on the domain of the function. So remember, what is the definition for relative extreme points? Relative extreme point, and the keyword is any other output in some open interval around C. So we say this point is actually a relative maximum point if the function value f of c is greater than any other point around this point, around it, then that's okay. But for the absolute maximum, the function is actually the condition is stronger, because here the condition is not just the points around our C, but actually every other output value, as long as the point you choose is actually in this domain, then you can just compare it with our target f of c. So actually you can see absolute maximum, this is a stronger definition than relative extreme point, than relative maximum point. And similar for absolute minimum, it is less than or equal to every other output value on the domain of the function. And then the next one, the output f of c is referred to as the maximum value or the minimum value. So this one talks about what does the f of c. If first we found the point c, and then the f of c is just called the maximum value or minimum. So next one, right here. If a function f is defined on a closed interval. So for closed interval, we use this one. This one means x is greater than or equal to a. So that means a is also in our domain. This is a closed interval. For an open interval is different. We can use a. This is an open interval. So for this open interval means the special point a, just the point a, that is not in our domain. It's out of our domain. But for an closed interval, a and b are in our domain. So the absolute maximum or minimum may occur at the two endpoints a and b. So remember last section we talked about the two endpoints a and b. They will never be the two endpoints a and b. They will never be the relative extreme points. But for this one, they can be actually, even though they cannot be the relative extreme point, but still they have the possibilities to be maximum, to be absolute maximum and absolute minimum. So this is the difference. For the two endpoints, even though they cannot be relative extreme points, but they can be absolute maximum or absolute minimum points, absolute extreme points. So this is a very important. This is the difference between section 4.2 and section 4.3. So from this one, we know that they can be. So do you feel like, all right, we will talk about it later. In the last part of this box is talking about how to find a relative extreme point on a closed interval. Still, now we are talking about a closed interval, not an open interval. So for a closed interval, compare the relative extreme values in the interval with the output values and at the endpoints f of a and f of b. So actually, first, this one talks about you can find a relative extreme point. For example, now we are looking for the absolute maximum point. So of course, the first step is to see if this function has any relative maximum points. If we don't have any relative extreme point, then you can just use the two boundary points, or you can just check the two endpoints to see if they are the if they can be the relative maximum, if they can be the absolute maximum point. And so the first case, if the relative maximum point does not exist. And the second case, if the relative maximum point exists. For example, we found two relative maximum points in this function. So, and then step number 2 is to compare these two relative maximum function values with the two endpoints f of a and f of b. If any one of them, f of a or f of b, is greater than both of the relative extreme points, relative maximum points, then actually we can just pick the boundary points f of a or f of b. And the largest of these values is absolute maximum, and the smallest of these values is the absolute minimum. So next, let's try to finish example 1. So finish example 1 in about 5 minutes. All right. So example 1a, you can see the two endpoints. So this one means actually this one means open interval. And what about the closed interval? So you can see the difference. Example 1 and example 2. This point means closed interval. You can see these two means closed interval. And this one, you can see an arrow. This means open interval. So that's the difference. And for open interval, that is like this one. So that means the 2 points A and B, they are not in our domain. And so for the first function, when x goes to infinity, the function increases without bound. The function also goes to infinity. And when the x goes to negative infinity, the function actually goes to 0. The first question, this is e to the x. Well, the first question, what about the absolute maximum? Do we have an absolute maximum point? Actually, no. For this one, you can see, because we don't have the boundary, the f of x goes to infinity. So, of course, we don't have the absolute maximum point. So we just say no. Then what about the absolute minimum? So some students may answer 0. Actually, if it is a closed interval, then we have an absolute minimum. But for this one, actually, the function goes to negative. When the x goes to negative infinity, the function goes to 0. But actually, we cannot find any special point, c, that f of c is just a 0. We cannot find that point. So that means we cannot find the absolute minimum point. And even for this function, we don't have a relative maximum. We don't have a relative minimum. And we don't have the two endpoints for us to compare with. So that means actually, for this one, we don't have absolute extreme points. And then next, let's check example B. Example B, all right, open interval. And the first one, absolute maximum point. No, we don't have what I want because both of them goes to infinity. So for the first one, we don't have. And the next one, what about the absolute minimum point? So for this one, from the function is obvious, so of course this one. And the first step, if we use this method offered in this box, the first method, is there any relative minimum point? Yes, we do. We do have one. Right here, this is a relative minimum point. And then compare this relative minimum point with the two endpoints. But actually, this one is an open interval, so we don't have the two endpoints to compare with. So the only winner of this match is just the relative minimum point, which is this one. So yes, where x equals to 0. And example 2. So pause the video and finish example 2 in 5 minutes. So for this way, for question 2a, 2a is closed interval. That means this point, when x equals to 0 and when x equals to 5.5 is in our domain. So that 2 points can be our options. So the first one, what about the absolute maximum? So for this function, do we have a relative maximum point? So relative maximum point, first question, how many critical points do we have in this function? We have only one critical point. Well, this is the closed interval function. So probably we don't consider the two endpoints. So all right, for this function, let's see this one if it is a relative maximum point. In any open interval, if we draw any open interval, any open ball, so you can see this point, actually the function value is higher, is greater than this one. So this is not a relative maximum point, even though it looks like a relative maximum point, but this one is not. And then since we don't have any relative maximum points, so we just consider the two endpoints. And then the first endpoint, all right, of course, this is not a relative maximum point because you can see this point, the function value is greater than that one. So this one cannot be a absolute maximum point. Then what about the other endpoint, this one? So from the function graph, this one is higher than any other points. So this is our absolute maximum point. That is x equals to 5.5, I guess. Or yes, x equals to 5.5. And the output value is about, it's about 60. And then nature of derivative. So the derivative at this point, the derivative of this point does not exist. And then about the absolute minimum point. Absolute minimum point. So the first question is point 3 a relative minimum point? And the answer is no. Because for this point, the function is not defined there. This is a whole, the function value f of 3 is actually there. And this is not a relative minimum point, because if you draw an open interval, then you can see the function is defined here. The function value here is actually lower than that one. So based on the definition, this is not a relative minimum point. So the relative minimum point, does not exist. Then let's check the two boundary points. This one is not a relative minimum point. It's not a It's not an absolute minimum point because this one is lower than that one, and this one is not also because we can find any other point in this function is actually lower than that one. So that point we don't have any absolute minimum point. Then let's consider the second one. The second one, this point we know this is a critical point, and this point is a relative. This point is a relative maximum point. So since now we have a relative maximum point, then for the absolute maximum point, let's compare this one with the two endpoints. So now we have 3 players, and we are looking for the point that is the higher, that is the highest one. That means higher than any other one. So actually, if you compare these 3 options, then this is the winner. So the absolute maximum is input value is x equals to 3, this one. And the corresponding output value is just y equals to 60. And the nature of the derivative does not exist because this is a sharp corner, and the derivative of a sharp corner does not exist. And for the absolute minimum point, this is we use the same trick. So for this one, this is the first critical point, and now we have the second critical point, because for this one, we have a horizontal tangent line. That means the derivative is 0. Derivative is 0 is then we know this is a critical point. And after you check it, then we know this is a relative minimum point. For the relative minimum point, and we want to know which one is absolute minimum point. So we have to compare this one and the 2 endpoints, this one, that one. And so which one is the lowest one? Actually, this one. So the absolute minimum point is just x equals to 1. Output value is y equals to 4. The nature of the derivative is just the 0 because we have a horizontal tangent line. And this is question number 2. Next, let's finish example 3 in 5 minutes. So for this function, you can see the function is defined on a closed interval. So that means the 2 boundary points. The 2 endpoints can be, they are in the function domain. So the first question, label each of the points at inputs A, B, C, D, E, and G with all that apply relative maximum, relative minimum, absolute maximum, absolute minimum. So let's see the first one, the point A. Point A, this point is higher than any other point in this function graph. So this is the absolute maximum point. And the next point B. Point B, the derivative at this point is 0, so we know this is a critical point. And this is a relative minimum point by using the first derivative test. And then the next one, C. Point C, derivative is 0, and this is a relative maximum. Point D, relative minimum. Point C, relative maximum. And point G, pay attention, point G is the endpoint. So we talk, in the last section, we talk about the 2 endpoints. They will never be relative extreme points. So for this one, first, point G cannot be a relative minimum or a relative maximum because G is the endpoint. And second one, what about the absolute maximum or absolute minimum? Based on the definition of absolute extreme points, the point G is none of them. So point G is not relative extreme point, and point G is not an absolute extreme point. And question number B, can absolute extreme point occur at an endpoint of a closed interval? So yes. This gives you an example that the first endpoint A is absolute maximum point. It's an absolute extreme point. And the question C, can a relative extreme, so let's highlight this one. Can a relative extreme point occur? No, because the 2 endpoints will never be relative extreme points. Next, please finish example 4 in about 8 minutes. So for this function, this is about the population of Kentucky can be modeled at P of X, where X is the input, X is the number of years since 1980, and pay attention to the domain. X is from 0 to 10, and this is a closed interval. So that means the 2 points 0 and 10 are actually defined, are well defined. And the first one, label and mark for the alright, this one is for the absolute extreme and the absolute minimum. So first one, the absolute maximum, that is easier to find. This is an absolute maximum point. The next one is, which one is the first question? Let's change the question to which one is the relative minimum point? This one, right? This is a relative minimum point. But the next question, which one is the absolute minimum point? It's not this one, because you have to compare the relative minimum point with the 2 endpoints, this one and that one, and find the lowest one, that is the absolute minimum point. So actually this one wins. So this one, the black one, is actually the absolute minimum point. And in section 4.2, so in section 4.2 for the that is one of the homework questions. make sure you know how to use your calculator to find the x and the y of the to find the relative extreme point of a function. So that means you have to know what is the input value and what is the output value. So question B is actually you just copy it from section 4.2. So this is the second opportunity for you to follow up with this part. So there must just make sure you know how to get the x p of x, and the second x p of x. So this one is all right. Then the next question example C, find the p of 0. So this one just the normal one. This is our p1 and p1 y1 of 0, y1 of 10. So y1 of 10, p of 0 is 3661, and the p of 10 is 3692. And from the function graph, this is the function graph, and this is the slope graph or the derivative graph. So you can see this is the relative maximum, this is the relative minimum. So for the relative maximum, the corresponding derivative is 0, and for the relative minimum, the corresponding derivative is also 0. The next one. So actually this one shows you if we are not given this function graph, we are not given this one, we are only given the function equation. How can we find the absolute extreme points? How can we find the absolute maximum point? And how can we find the absolute minimum point? So this is a very good and a very important example. So make sure you know if we are not given the function graph, how do you find the derivative? How do you find the absolute extreme points? So this shows you how. So from step B, first use your calculator to find the relative maximum and relative minimum points. And the next one, because for the absolute extreme point, we have to compare if we have relative extreme points, we have to compare our relative extreme point with the two endpoints, the function value. So next, we have to find what is the function value. That is our step C. The two endpoints, first one, 0, because it is from 0 to 10. So the first one is 0, the second one is 10. We have to find the corresponding function value. The first one, p of 10. p of 0 is 3000, this one, and the p of 10. So next, we have to compare this one and this one, So that is step D. After our comparison, the first one for the absolute minimum point, we have to compare our relative minimum point. This is the function value, and compare this one with the 2 one, and find the lowest one. So actually, you can see here, number 1, number 2, number 3, because we are looking for the absolute minimum point. So this one wins. So that means you have to change your corresponding x. That is 0. When x equals to 0, we have the corresponding relative minimum, absolute minimum point. So the absolute minimum point is just 0, and the 3661. Next one, what about the absolute maximum point? We have a relative maximum point, that is right here. The function value is right here. And then we have to compare this one with the two function values and find the highest one. So the number 1, number 2, and number 3, 3 players. This one wins. So we doesn't change. Our relative minimum point is just our absolute minimum point. And the interpretation between 1980 and between 1980 and 1990, Kentucky's population was lowest. Lowest just means the absolute minimum point was lowest in when x equals to 0. So x equals to 0 means 0 years since 1980. So it's just in 1980. at which time the population was. So the first step, this one means what is the input, and the next one, what is the output, including the unit. Unit is 1,000 people. And similar, highest means the absolute maximum point. It's 1984. Oh, excuse me. Pay attention to the difference with these two questions. The first one is in year 1980, and the second one was how many years after 1980. So this is tricky. So that means we have to choose the x value instead of x plus 1980. So it is just a 3.156. And the corresponding value is just this one, 3,702. And the unit is 1,000 people. Then we are done. Let's try one more example. Example 5. So the first question, write a sentence of interpretation for the other pair. So this is the normal one. It's not tricky. At approximately 2. So for this one, we just plug this one in. The input number t means t hours after 9 p.m. So you just plug in 5.612. We use 0.612 times 60 minutes. Then you will get like the minute. Then the answer is 2 a.m. 37. This is the input. And the output means percent gives the percentage of the people, blah, 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 this part. So just say 96.356% of people aged 15 and older in the United States are sleeping. Alright, this is about the interpretation. And next question, what is the absolute maximum on the closed interval from 0 to 10, from 0 to 11? And for this one, we are given the function graph. So make sure you know, if we are not given the function graph, you know how to get the absolute maximum and the absolute minimum point. And similar, this one, I just give you the answer. The absolute maximum, this one is not tricky at all, 5.162. So make sure you can get the exact number. And the answer of T is 96.356. So again, make sure you know how to get these two numbers by using your calculator. And the details is actually in the last section. And the interpretation, this is about the interpretation. Occurs 5.162 hours after 9 p.m., which is about, at which time 96.356% of people 15 years and older are sleeping. And the next one is about the absolute minimum point. This one is tricky. This one is just 0. So think about why it is 0, not the relative minimum point. And S of T is 13.52. And similar, 0 hours is 13.52. So actually now we're done with the lectures. And the homework for the section is example 6 and example 7. So again, you can just send me the picture of this page. Or you can just this one. Or you can just write it on a piece of paper and send me the picture of your answer. So as long as you turn it in, you will get full points. This is the second one. Alright, and feel free to ask if you have any questions. And again, the office hour is every Monday, Wednesday, Friday from 11 to 12. That is our class time. If you have any questions, send me an email, then we can just talk about the questions in Zoom. Alright, thanks for watching.